How are you doing, Professor? This is a presentation for our project. Our project topic is FaceNet and Android. In this presentation, we will briefly introduce the objectives of our project, how our system works, and how our system be implemented. In the end, we will show the evaluation for our system. In our project, we first want to build a FaceNet model with good performance. This FaceNet model can calculate a mathematical representation of face that can be used in machine learning tasks, like classification and clustering. Then we want to develop an Android application that performs real-time face recognition by making use of FaceNet model we built. In addition, we want to do some evaluation for our system, like the accuracy of our FaceNet models and the execution time of FaceNet part and face recognition on Android device. Then let's see how our FaceNet Android application works. This diagram shows the system structure of our FaceNet Android application. Once the application is started, the rear-facing camera will continuously send preview images, and then the camera preview is continuously shown on the screen. The camera source component manages receiving these images and passing the images into the face detector. Once the face is detected, some graphics will appear on the screen, indicating the position of detected face and associated facial landmarks. With the help of control panel, that is UI interfaces, the training mode and classification mode could be enabled by the user. This diagram shows how the training mode and classification mode work. When the training mode is enabled, once the face is detected, FaceNet part will calculate a 128 dimensional unit vector representation of the face. This vector and its corresponding person name that is specified by the user will be saved as training data. For each person, they need to collect at least 10 face bitmaps. After training set is built, the application will build a classifier which will be used in the classification mode. When the classification mode is enabled, once the face is detected, FaceNet will calculate a new 128 dimensional unit vector. Then the classifier we built in the training mode will be applied to this vector and output the predict person name. This diagram shows the workflow of face detection and FaceNet log in the previous slides. Each video frame will be passed into the face detector. Once the face is detected, the application utilizes the information of the face, including position, face width, and face height to crop a face bitmap and resize it to 96 multiplied by 96 pixels. Then this bitmap is normalized and then passed into the FaceNet model. This FaceNet model can represent the face on the 128 dimensional unit vector.
Okay, and then I will introduce about the implementation of our FaceNet system. Our implementation of FaceNet system is divided into 4 parts. First one is the UI and preview. Second is the camera work, and third is face detection on Android, and last is classification on Android. First one is the UI and the preview. The UI of our FaceNet is mainly divided into 3 parts: camera source preview, control panel, and the graphic overlay. Camera source preview can get the view from camera and then show it on the screen of the Android device. Control panel shows some control bars on the screen to let the users control them on app. And graphic overlay is used to show the facial landmarks and bounding rectangles on the screen. All user interface elements in an Android app are built using view and view group objects. A view is an object that draws something on the screen that the user can interact with. A view group is an object that holds other view objects in order to define the layout of the interface. Camera source is a view group, and camera panel and graphic overlay are view. There are also two ways to declare the layout in the code. First is declare UI elements in XML file, and the second is the instantiate layout elements at runtime. Camera source preview and graphic overlay are using the first way, and the control panel is using the second way. Second is the camera work. We use camera source library to implement camera on our Android device. Camera source is a computer vision source which can have conjunction with face detector and send preview frames for detection. And the steps of working of camera are shown in the slides. The first one is the detect and access camera. We should create code to check for the existence of the cameras and get camera use permission. Second, we should create a preview class that implements the interface. This class previews the live image from the camera. We call it camera source preview in our project. Third one is enable camera source preview in main activity. After calling the preview class we create from second in the main activity, we can see the view of the camera. The fourth one is setting up listener for capture. Connect the training switch listener to the take picture function. Capture the frame every time after user switch on the button. The last one, after the life cycle of our main activity ends, we should release the camera. And third part is the face detection on Android. In our project, we utilized Vision Face API in Google APIs for Android to detect face and associated facial landmarks. The face detector is created in the onCreate function of the app's main activity. In the builder for creating face detector instance, we choose accurate mode to acquire high accuracy in the performing face detection. Since our Android application performs detection on live images, we also have face tracking enabled, which could give a more accurate and faster result. In addition, we enable facial landmark detection and an additional classifier to determine whether eyes are open or closed in face detector builder. In addition, in order to indicate the positions of the detected face and associated facial landmarks, we draw graphics over the detected face by using Canvas class in Android Graphics API. The right screenshot shows the result of face detection on Nexus 5X. The last part is the classification on Android. In our project, we utilize Weka, a collection of machine learning algorithms for data mining tasks, to perform classification of the 128-dimensional unit hypersphere representation of the face. The algorithms that are provided by Weka can be directly called from our own Java code after we import the Weka Java file into our Android project. In order to achieve classification via Weka, we first build a feature vector with 128 numerical attributes and a class attribute that use the person name as its values. Then we build a training set by adding array list and that contains 128-dimensional unit vector presenting the face and a array list that contains corresponding person name. In the end, we build a classifier based on the training set that we create and use it to do the classification for the incoming new data.
For the deep learning part, first we train a FaceNet model in TensorFlow using Python API. In the FaceNet model we train, the input are two tensors, the input image and training flag. The input image is a tensor for four-dimensional image data. The training flag is a tensor of a single binary value. We can set it to true when we want to enable training, and set it to false when we want to do testing.
Since in TensorFlow, each weight in the graph is stored as a variable instead of a constant. So, and it makes training or updating the existing graph become much more convenient. So the training flags here can take good advantage of the TensorFlow characteristics. After validating the performance of this model, we transform the checkpoint file, which stores the model, to a protobuffer file. This file contains both the graph definition and weight of our model, and they are accessible in the TensorFlow C++ API. We make inference in C++ and use GMI to return the embedding result. Next is our results. We test the FaceNet model on both LFW and self-capture datasets. The accuracies are all above 90%. We also reduce the dimension of the embedded vector from 128 to 2 and plot the result here. It shows that the face of different people are clearly separated. Our self-capture dataset composed of 166 faces for 5 students. This dataset has faces with different emotions, decorations, makeups, perspectives, and lighting conditions. We think it can reasonably simulate a complex situation in real-life scenario. This dataset is collected by the app automatically. Then we will also test our whole system on different datasets and train different classifiers to see their performance. Generally, the cannon has good performance and less computational time. This is because that the size of our dataset is really small. If there are thousands of people, millions of faces images, the computation time grows polynomially. The multi-layer perceptron is a naive version of deep learning model. It can achieve extremely good performance with only one hidden layer of 10 neurons. The decision tree and LDA method have medium performance and relatively long computational time. In the end, we measure and approximate the computation time for the whole system. According to this table, the computation time for FaceNet in GNI on Android platform is about 60 milliseconds, and the total time for classifying one image is about 150 milliseconds. For the future work, we will keep track of the TensorFlow issue, which hinders our Android implementation for FaceNet, and also investigate training network on mobile devices, as well as the GPU utilization. And that's a brief overview of our project. Thank you.